Great, thank you. It's a pleasure being here. This is a big room tonight. This is fantastic. Thanks for that introduction. In my position at SGH, I rehabilitate existing structures. I investigate structures that have in some way failed to meet somebody's expectations. But for the most part, I design new building structures. So I'm involved from the very start of the project through design coordination, construction administration. You can see me in the lower left looking very studiously at my clipboard. And occasionally, I get to see the finished product. This happened to be near our office, so I actually got to see it when it was done. That almost never happens. But my head is very much also in sustainability and resilience. I'm the secretary of Committee 130, which is in the process of preparing a sustainability guide for concrete. And I'm one of the task group leads for 318 Subcommittee N, which is drafting sustainability requirements for an appendix that we hope will be in the 2025 edition. So in my professional practice, I'm very interested in resilience of structures, whether that's helping owners navigate the rising sea level we have in the Seaport District of Boston, putting up flood barriers, as you see here, or helping owners understand the snow loads on their roofs of critical structures. So in my presentation today, I'm going to address the challenges of sustainability from the designer's point of view. I'm really glad to have this opportunity to be on this panel with all these folks who know a lot more about concrete chemistry than I do, about people who actually place the concrete and order the concrete and get it delivered to the site. So I'm anxious to hear what they have to say as well. So when we design buildings, we often do so, unfortunately, in a vacuum, without the perspectives of the folks who are going to deliver the product to the site, who are going to actually build it. So I'm going to start off talking tonight about embodied carbon and the SE 2050 commitment, and how we can, but don't always, calculate the embodied carbon in our designs. I'll spend most of my time talking about concrete specifications and reducing embodied carbon in our content, as well as conserving resources in the process. And I'll wrap up by talking about some of the threats to innovation and how it's hard to fight the system that we have in place right now. So why do we as engineers need to focus on embodied carbon? Well, it's really quite simple. I mean, building construction accounts for about 10% of the global emissions, and that was in 2019. That was sort of the most recent normal year before COVID hit us, and I suspect that we've rebounded from that and gone perhaps beyond that. Overall, buildings account for 38% of global emissions, and that includes building operations. So about 28% or so is operations, 10% is building construction. And as I said, I've selected this data from 2019. I assume things have changed a little bit since then. According to the same study, concrete alone is expected to contribute 12% of global greenhouse emissions by 2060. So this is something that we need to address and need to address quickly. So about the SE 2050 commitment, the challenge for this was issued by the Carbon Leadership Forum in 2019, and then formally developed by the Structural Engineering Institute of ASCE. And simply put, it is imperative that all structural engineers understand, reduce, and ultimately eliminate embodied carbon in our projects by 2050. We must, and so as signatories to this pledge, we have to every year submit projects which we do a whole building life cycle assessment on to determine how much embodied carbon is in them, and then we are compared against our peers anonymously to see how we stack up against them. So this gives us the opportunity to understand how we're doing and what we can do to improve upon our work. So in terms of actually how we calculate how much embodied carbon we have in our projects, we use a whole building life cycle assessment approach. And at SGH, we have three methods that we're using to do this. I give my colleague Mark Webster credit for this. We have a program for Revit called Tally, which allows us to extract data from our Revit model. For those of you who don't know what Revit is, it's a building information modeling system, and it's effectively a database whose output is drawings that we give to the construction contractor. But it really calculates quantities of materials. We can extract those quantities of materials and evaluate them for their global warming potential and use that to evaluate our structure. There's also the Athena Institute's Athena Impact Estimator for buildings. That's a standalone product, which we can insert our quantities manually. And then we are in the process of developing an internal calculator, which will, similar to Tally, extract data from our Revit model and use that to evaluate our structure. So, but, of course, this all depends, the calculations depend on what we choose to model in our Revit model. Right? We don't model the whole structure. We don't model every nut and bolt. We don't model every gusset plate. We don't model every concrete curve. So there's some loss of data in that process. So for any project, large or small, we develop some form of concrete specification document. It doesn't always look like the one on the right. This is an example of one. And through the specification, we describe the requirements we have for the project, and we also establish our sustainability goals for the project. But who has time to read the specification? I mean, this is part of a 4-volume set of thousands of pages. Who's going to read all of this? Well, I really hope that the concrete contractor reads this before he or she puts his or her bid in place. But it's a big document, and hopefully before the bid. And what I found quite recently is that nobody really reads it until there's a dispute later on in the project. So something to keep in mind. So because of this problem with nobody reading the spec, or until it's too late, we started putting it directly on our drawings with the mixed design table, something like what you see here. This is just an example. Don't get too excited about it. And we'll dig into this here in just a moment. Before I do, I want to talk about environmental product declarations. So starting now and into the future, our concrete specifications will require that concrete suppliers submit an environmental product declaration with each of their mixes on the product. So what is an EPD, or an environmental product declaration? It's effectively a nutrition label for concrete. It describes 6 primary environmental impacts, and this applies to any building material, not necessarily specifically concrete. Global warming potential, which is really the thrust of what we're concerned about, GWP, and I'll talk more about this in the next slide. Ozone depletion, acidification, smog formation, eutrophication, which is water contamination, which causes algal blooms and increased bioactivity in water, and primary energy demands. So NRMCA has started developing these on a regional basis, which we often use early in our projects to figure out what our carbon budget is when we do our whole building life cycle assessment early in the design. Some concrete contractors have started preparing their own product-specific EPDs, and those would then be part of the submittal they make to us. And then at the end of the project, we can use that submittal information to rerun our life cycle assessment and see how we did. So digging back into the mixed design table a little bit here, you will see that we've listed maximum values for global warming potential, right down here, GWP, that's measured in kilograms of CO2 equivalent per cubic yard. And we're also including maximum Portland cement content. So don't read too much into these values. These are examples. As a company, we haven't decided really where we need to end up on these. So this is something that's currently under discussion. But you'll see that we're including Portland cement content as well, and a maximum limit on that. And there's one reason for that, and that is for concrete contractors who may not have an EPD for their product, or for which we can't get a regional EPD that's appropriate, that the maximum cement content is effectively a proxy for global warming potential. So, but what limits should we set, as I said? Where does this fall? So for maybe a 5,000 PSI mix with 620 pounds of cement equivalent, 495 pounds of cement is probably equivalent to about a 20% SCM replacement. So the question is, does the ready-mix supplier have EPDs to compare to these limits? And what do the Portland cement limits we have here influence on pumpability and finishing? And how do the Portland cement limits influence durability, particularly with the exposure class that we have to deal with? Another way we can reduce embodied carbon, as Kevin alluded to, is by using a finely interground limestone with our Portland cement, maybe up to a 15% replacement using ASTM C595. Basically as an interground filler. And it's my understanding that you can have really minimal or equivalent concrete strength with these mixes. But the question is, does the ready-mix supplier have access to C595 blended interground cement? Have they done the trial batches or strength tests that we would require as demonstration with these mixes to demonstrate that this is acceptable for our project? And what effect does this have on the flatwork finisher and placer? Do they have experience with these mixes? As Kevin mentioned also, we can replace portions of our Portland cement with things like fly ash, or slag cement, or silica fume, or ground glass pozzolan. But is it available locally? What cost is that to the project? How does that compare to the Portland cement? And where do they come from? And as a sort of a mini case study, going back to the second slide I showed you with the bright orange and white building, that project was going for a platinum certification. And with that, we also had a requirement for regional materials, as you might imagine. And the concrete supplier dutifully read our specification and provided a mix design which included fly ash from Italy. So we ended up accepting it. There's nothing wrong with the fly ash, and the real problem was on our end of things. We were designing this building in 2017, and in 2017, the Brayton Point power station in Somerset, Massachusetts, which was the only coal-burning power plant in Massachusetts, closed down while we were in the middle of design, and leaving only one or two coal-burning plants left in New England, all of which burned a variety of fuels and didn't provide fly ash that was suitable. So all of our fly ash came from Rome. So I'll add that even with the shipping costs and the increase in embodied carbon due to the shipping, there's probably still a good benefit for us to having used fairly decent fly ash replacement. Another way to potentially reduce the cement content while sequestering some carbon dioxide in your cement paste is CO2 mineralization. So we can sequester maybe a pound a cubic yard, depending upon the cement content. I think I have that right. But the real benefit to this is that you may be able to reduce your cement content by 20 to maybe 40 pounds per cubic yard, depending upon the mix design and the requirements. The catch, of course, here is that it's not available everywhere. There are no providers of this in the New England region, so I can't use it on any of my projects in Metro Boston yet. And the other thing is, can the mix tolerate a reduction in cement and still maintain pumpability? Shifting gears a little bit from the embodied carbon, talking about some other important resources. Concrete uses a lot of water. Not only in the mix itself, but in washing water for the mixers. And there's, of course, water on the site at the concrete ready mix plant that needs to be dealt with. So maybe we can reclaim some of this water and use it in our mixes and not specify potable water. But does the ready mix supplier have access to the testing required to make sure this water is suitable for the mix? It may be contaminated with chlorides from de-icing salts on the site, or sulfates or alkali. And does the ready mix supplier have the means to store this water and capture it for reuse? Also looking at another resource, virgin aggregates are being depleted, so maybe we can find a way to recycle some concrete and turn it into aggregate for our concrete, new concrete. It's the heaviest portion by weight, so let's give it a try. So there are two main sources of this: concrete returned from the batch plant, I should say, and concrete that's salvaged from existing demolished structures like buildings or bridges. And you can also use crushed glass aggregate to some extent too. But does the ready mix supplier have access to and room to store the recycled concrete aggregate in the yard, in addition to the virgin aggregates that he or she already has to store? What are the sources of the recycled concrete aggregate? Is it coming from a building site that's potentially contaminated, or that has chlorides in it because it was formerly a parking garage or a pavement? And how do we trace the provenance of those recycled aggregates? And what about pre-production testing to establish strength? You have to be on this very early in the process, perhaps even during design. And so maybe a design been built to process without a CM involved early. It's going to be hard to do this on. Another way we can try to minimize the volume of cement paste and survey is the tarantula curve, and trying to optimize our aggregates and minimize paste volume. But what if the aggregates supply mix provider does not have access to the right aggregates in the right sizes to reduce the paste volume and how do we as the designers specify the right aggregate gradation to make the most of it. We can also look at extending the time that we require to achieve the required strength. So maybe we're looking at 56 days for foundation elements, whereas we've maintained 28 days on our elements that will see more load early in the process, because maybe the owner and the contractor schedules can't accommodate a longer time to develop their strength like they would on, say, a suspended slab. So where I end up with all of this really is that the specification sometimes becomes something more of a wish list than a requirement. The contract sub is often on board long after we've written and submitted this, and of course the concrete sub needs to get going very quickly in the project, and so the materials, the testing that's required to back them up may not be available in the time that's available to get the job going. I'm going to take a slight detour for a few minutes here and talk about some threats to innovation. And one of those is concrete testing during construction. We all rely on our cylinders that are cast on the site to give us some idea of what the concrete material that's actually in situ is. Right? But there can be quite a bit of variability between what's actually in situ and the cylinder that is taken at the back of the truck. There can be variation in the preparation of the cylinders to the site, storage and handling of the cylinders, and preparation of the cylinders for testing whether they're properly capped or not, and variation between different technicians on different days who come to the site. So there's a real risk here that if things don't go right with the testing, there can be delays to the project. There's our time to investigate what might or might not actually be a low-strength concrete. How can we possibly accommodate a true low-strength break if we actually have one? And who pays for the investigation to determine all of this? And what happens to the schedule in the meantime? So those are some of the risks of the low-strength break. And this is really a result of the industry system. There are enormous risks to the concrete supplier and contractor for low strength, and no rewards for just barely making the strength each time. Why would they risk it? So one set of bad breaks could cost them all of their profit for the entire job, and I understand that. And one of the consequences for the risk of a low strength break, whether real or perceived, is there's a tendency for suppliers to over-cement their mixes from time to time. I'm not saying it happens every time, but I'm seeing frequently in my test results that I'm getting back, and this test is about a month old, 5,000 PSI mix, hitting 5,300 or 5,400 at 7 days. I'm not saying this is necessarily that. ACI 301 would require us to have some mixes that are well above the threshold, but I'm finding increasingly common that I'm seeing those high-strength breaks. And so I think that really comes down to some of the perceived risks in the project as well. For all the stakeholders, for the designers, the concrete suppliers, the construction managers, the owners, is the importance of schedule really is paramount. They really need to get into their building and get the work done as quickly as possible. And there are fee pressures for the designers. Why should we spend the time to innovate when there are risks associated with that? There are a lot of incentives to do what we did yesterday, what we've been doing for 100 years. And there isn't necessarily as much incentive for us to take the risk. So that's one of the things that I'm personally struggling with. I'm anxious to hear what the concrete suppliers' take on this is. So thank you all for your attention, and a quick thank you to my SGH colleagues who helped me with this: Mark Webster, Matt Sherman, who's here in the front row, Pedro Cifre, and Julie. Thank you.